Welcome to Practice Class number 155. Today we're talking about how drones aren't as efficient as what you might expect. And what we will cover applies to pretty much all drones and aircraft in general with more than one rotor. And we will be covering perhaps the most extreme case in this podcast. And the word drone refers to any aircraft that is unmanned, but what we will be discussing today doesn't really matter whether the aircraft is manned or not, as long as the aircraft has more than one rotor, and the same shortcomings will occur in the efficiency regardless of that. You can have a no person, a person, or even a Lego man as a pilot. So drones are great. They are very easy to use. They are stable. They can hover and they can carry quite a large payload, considering how much they weigh especially. Another major advantage is that because they are very stable, images taken with cameras are quite good quality, which is why drones are very popular among the Peeping Tom community. All of these benefits are due to the multi-rotor system. A very common configuration is 4 rotors, 1 at each corner, but you can get 5 rotors, 6 rotors, or even 8 rotors quite commonly. So this podcast is looking at how all of these rotors affect each other, because when you start putting them quite close together, obviously they're going to be throwing air into each other, and will that affect them? And even just having them in close proximity, when you have air going into them, they then start to accelerate the air around them, and that can change the efficiency potentially. So in other words, if you get 10 newtons of lift out of each rotor, what happens when you put several of them around the aircraft? Do they interfere with each other? Do you still get the same amount if you just summate them linearly or not? And if so, how much does it affect the performance? So to look into this, we're looking at this aircraft here in figure 1. It has 4 rotors at each corner, so these green ones, 1, 2, 3, you can't see the one behind here, and 4. And it also has 1 major rotor at the top, like a helicopter, and then 1 pusher rotor at the back, which we can see a bit better in this figure 2 here. And the great thing about this paper is that these researchers looked at all these different combinations of when these rotors are working. So they looked at when you have just the top rotor working, you have it with the rotor top working and the 4 corner rotors, and then also at different power efficiencies as well. So that's quite nice. And I should mention that actually this paper is called Measurements of Aerodynamic Interference of a Hybrid Aircraft with Multi-Rotor Propulsion. So we can see it just here, the title, and it is open access as usual. So you can find a link in the description if you want to play along at home. So in figure 2, let's just go back down to figure 2 where we saw the aircraft. On the right side, we see that this aircraft has a horizontal stabilizer, so this white part here going along here. And this is in a boom configuration. If you don't know what the boom configuration is, it is when you have the horizontal part of the tail connected to the fuselage with 2 poles, 1 on each side. So you can see here 1 pole coming out from the left and 1 pole from the right, and it connects in this kind of configuration. But something that is a little strange about looking at least of this horizontal stabilizer is that it looks to be a little wonky. I mean, is it just me, or does it look like the tail is not quite level? It's kind of sloping down a little bit at one side here. I don't know if this is actually the case, or if it's just the camera angle that makes it seem like it's not level. Anyway, the great thing is that these researchers looked into how the different rotors affect each other with an efficiency of these rotors with the aircraft experimentally, which seems like forever since we've actually had a paper that wasn't CFD, so I'm excited about looking at the experimental side. So in table 1, we have the accuracy of the load cell that they used. So they put this aircraft onto a load cell in the wind tunnel, and then they measured the forces coming off there. And they give the accuracy of it. And there are a couple of things that we should discuss about this load cell accuracy and how they present these numbers here. The first is that they say that the average relative error is etc. And one nuance about any measurement is that when you report what is commonly referred to as the error, you're actually reporting the uncertainty. And the reason why this is because you don't actually know what the error is. If you did, you could simply offset all of your measurements with this error, and then there'll be no error because you just factored that in. So more accurately, what you're saying is that the actual value lies somewhere between the measured value and then the range plus or minus the error that you reported. So this is actually uncertainty because you're not really sure where the value lies in this range, but you're certain that it is within this range. So that's why it is uncertainty and not really error. And what's more, when we give the uncertainty, or what is commonly referred to as the error, it is also important to give the confidence interval. So if your data fits a bell curve, also known as a normal distribution or a Gaussian distribution, you can accurately find the standard deviation of your data. So what that means is that, let's say you have your measurement, you have your object there and you're measuring 100 times the value in a certain configuration, then you plot them all onto a bell curve. You can then figure out how much they're deviating along and find the standard deviation of that. So By using statistics, you can then tell the reader that you are sure to within a certain limit that the measurement lies in this range. For example, let's say that your standard deviation is 0.5%. That means that the value you measured, plus or minus 0.5%, means that you are sure to within one standard deviation that your actual value lies within the value you quoted, plus or minus that 0.5%. So what that means is that you are 68% sure that your value lies within this range, because that's what the standard deviation means. If you go one standard deviation away from the mean, that's 68% confidence interval. If you get two standard deviations, then you're 95%, and then so on and so forth. So if you take the range from the quoted value minus one standard deviation or plus one standard deviation, you're encompassing 68% of the values. And if you take two standard deviations, you are encompassing 95% of the values, and 3 corresponds to 99.7% of the values. So just saying that the uncertainty is whatever isn't enough, because it doesn't take into account how certain you are. So are you 68% sure, 95% sure, or 99.7% sure, or something else? You can use 2.7%. You can use 2.7 standard deviations, for example. You don't have to use exactly 1, 2, or 3. You can use whatever you like. So for example, return to the last example where you said that the standard deviation was 0.5%. So saying that the uncertainty is 0.5% really only means that you are 68% sure that your actual value lies between your measured value plus or minus 0.5%. But if you wanted your results to be more robust, you would select more standard deviations, for example, 2 standard deviations. So now you would say that the uncertainty is plus or minus 1%. And what that means is that you are 95% certain that the true value of this measurement, what it should be, lies between the measured value that you got, minus 1% and plus 1%. And you can get more and more stringent if you like. The point is that quoting this uncertainty, or in this case labeling it the error, isn't a complete way of describing it, and you also need to say the level of certainty. For example, is it 68%, 95%, 99.7%, or something different? Not doing this can lead to wrong conclusions being drawn, simply because you might think that a trend exists, but in reality, it was just that your uncertainty level was too small. Perhaps you only chose one standard deviation when you should chose 2. So moral of the story is that anytime you give the error, you should really call it the uncertainty, because that is the more accurate term, and you should also give the confidence interval, whether that is 95% or whatever. The most common confidence interval is 95%, which corresponds to 2 standard deviations. The second thing I want to talk about with these measurement uncertainties is that they give the uncertainty as a percentage of the full-scale range. Now, it is incredibly common for manufacturers in particular to say that their error in their, or their uncertainty in their load cell, I should say, is, they don't usually say uncertainty, they usually say error, but the uncertainty in their load cell is like 1% of the full-scale range. But it is quite annoying to have that, because you then have to do an additional calculation to find out what the error is for smaller measurements. Also, it doesn't really give any information about how accurate the instrument is when measuring values much lower than the maximum possible. To illustrate what I mean, let's say you have a load cell that can measure up to 100 newtons. At this point, the 95% uncertainty is 1%. What that means is that if we were to measure 100 newtons, we are 95% confident that the true value is between 99 newtons and 101 newtons. Now that is pretty accurate, but if that is the only information given about the accuracy, what does that mean if you're only measuring 10 newtons? Does that also mean that at 95% certainty, the 95% certainty is plus or minus 1 newton? If so, then that is terrible accuracy at this measured value of 10 newtons, because now you're saying that, okay, the actual value is between 9 newtons and 11 newtons, which is a 10% uncertainty. That's a really huge uncertainty. It's a potentially huge error. So now if you've ever used a load cell, you'll probably know that even though they are quoted to be accurate, let's say to 1% at full scale, when you go to much smaller values, the accuracy is still really good. It's just that you don't know exactly what it is, but the repeatability is definitely there. That's why giving just one number and it being the accuracy at full scale isn't that useful. It's far better to give the accuracy across a range, or to give the uncertainty as a percentage of the actual value measured and not the full scale value. So for example, you say it's plus or minus 0.5% on average across the entire range, which means that if you measure at 10 newtons, you know it's plus or minus 0.5%. If it's 100 newtons, it's still plus or minus 0.5%. So anyway, that is a little crash course in errors and uncertainties. Let's move on to the experimental setup here. So the researchers put this aircraft into a wind tunnel that had a cross-section of 1.5 meters in diameter. So yeah, it's circular. And I'm not really sure how big the aircraft is. I tried finding it here, but I can't see anything specific about it. The only thing I could really find is that the main rotor is 10 inches in diameter, so this major bit here, so 25 centimeters. And from the pictures, I guess that means that the entire aircraft is about 25 centimeters long and about 10 centimeters tall and about 20 centimeters wide. But these are just rough figures. So I'm not sure what the blockage ratio exactly is, but also the size of this particular aircraft is important because it is a rotary aircraft. The reason why the wind tunnel dimensions and the blockage ratio is even more important for rotary aircraft is because of how the air moves through the rotary system. What happens is that the air gets thrown down, so each one of these propellers, let's take the big propeller to begin with, the air gets thrown down and it can hit the ground, and that creates a massive ground effect. And if you have the ground there too close, you will get that ground effect. If you remove the ground, what actually happens is that the air goes down and then it cycles back up and then gets fed back down into the rotor and takes that motion. If you put the ground there too close, it messes with that motion, and you also get a much greater lift being produced. And rotary aircraft can really benefit from this ground effect as well. That's why knowing the exact dimensions of this aircraft compared to the experimental wind tunnel, etc., is, and where it was placed in the wind tunnel, is important. So anyway, these researchers looked at this aircraft in three different configurations. They labeled them K1, K2, and K3. So K1 is where the main rotor, so the helicopter bit here, plus the pusher propeller were operated at full power, and the four corner rotors were also operated but at only 50% power. So these little ones here were only at half the power. K2 is exactly the same, but the corner rotors were now operated at full power. And K3, the configuration K3, is just the helicopter bit rotating around, so no pusher and no corner rotors. They also completely removed the corner rotors and the supports for this configuration K3, so they wouldn't have like the interference of the air coming down into these arms, so to increase the efficiency of this rotor generally speaking. So figures 5, 7, and 9 give the lift. Let me go to these ones in a sec. Give the lift, so figures 5, this one, 7, this one, and 9, they give the lift, side force and drag, lift, side force and drag coefficients, Kz, Ky, Cz, Cy, and Cx respectively. Now figures 4, 6, and 8 give the overall forces, but we're going to look at the coefficients because that's a little bit easier to understand. They're more relatable and repeatable. Effectively, you can transfer them from different aircraft. So now these graphs show the values for when the fuselage was positioned at different angles of attack in the x-axis here, and this is to simulate flying forward and backwards. The minimum angle of attack was minus 13.5 degrees and the maximum was 0 degrees. So looking at the lift coefficient CZ, the orange line here, adding more rotors definitely increases the CZ, but interestingly there was a nonlinear effect. So first of all, if you look at this orange line here for figure 9, this is where we just have the K3 configuration, so only the helicopter bit, no other blades. When at 0 degrees, the lift coefficient was about 0.19. Now if you were to put the blades, all other blades on there, so the pusher and the corner rotors, and put it to maximum power, figure 7 here, we get at 0 degrees, the lift coefficient is about 0.4, so more than double. So obviously putting more rotors on there helped the lift that's expected. But in terms of the nonlinearity, in figure 9, we see that the results when we only have the main rotor here, going from minus 13.5 degrees to 0 degrees, didn't result in a linear change in lift coefficient. Instead, it is somewhat curved. So for example, at minus 13.5, the lift coefficient is about 0, but at 0, it's 0 degrees angle of attack, it's about 0.19. However, when we have the main rotor, pusher, and the corner rotors at 50%, so figure 5, the amount of lift produced at different angles of attack is now linear. So I'm not sure exactly why that occurred. It went from non-linear when we just have the helicopter blade to now linear. Then when we put the corner rotors up to 100% power, this is in figure 7, the relationship again becomes a little bit non-linear. It's still fairly linear, but not as linear as when we had the rotors at only 50% power. And we'll revisit this in a little bit in the end of the podcast. So as for the drag coefficient, these values are given by the CX line, so the green line. And when we only have the main rotor, so figure 9, the drag coefficient is very non-linear again, and almost a drag bucket forms. So this is where the drag coefficient at minus 30.5 degrees is slightly higher than at minus 8 degrees before shooting back up at 0 degrees. So there's actually a sweet spot here where we get the lowest drag, and that means that if you want to maximize or minimize your drag, then you can just flight this angle of attack. In terms of lift to drag ratio, you're going to have to find a different angle probably to maximize that. So this nonlinearity is preserved when you add corner rotors. So in figure 7, we still get that nonlinearity. It's not forming the drag bucket, but it definitely isn't linear anymore. And figure 5 as well is still fairly nonlinear. I should also mention that these lines are best fit. In some situations are very good. So for example, this situation and this configuration. But when we have the rotors at only 50% power, we have these dots fairly spaced off them. So this line of best fit is not that great here. The R² value is fairly low. So what this means in terms of the drag is that as you pitch the aircraft up, the drag coefficient continually increases for when we have the main rotor and the corner rotors working together. The reasons for these nonlinearities are a little unclear, but it is possible that it's to do with interference between the various rotors. So let's move on to the next section and see how they interfere with each other. So in the discussion section, now we get to the really juicy bit, the bit that we were waiting for. Let's go down to the discussion bit. So this section here is where we're going to find all the juicy bits we're after. So in the discussion section, these authors say that the main rotor, the helicopter bit, just by itself and no other rotors active, produced a lift force of 18.2 newtons by itself. This is what they said here. For the corner rotors, when they are operating just by themselves at 50% power, they are producing a 12.6 newton force, lift force. And when you boost them up to 100% power, they are now at 28.7 newtons. So interestingly, doubling the power of the corner rotors more than doubled their lift generation. And I think that it may have something to do with the Reynolds number in this particular case, and possibly the ground effect. So to begin with, the reason why I say ground effect is important here is because I don't know exactly how close it is to the ground. So I don't know if the ground effect was occurring here. If it did, then it makes sense that when you double the power, you get more than double the lift because you are forcing more air into the ground, but it can't escape. So you get this additional boost, and the reason why it could be nonlinear is because at 50% power, perhaps the amount of air thrown into the ground wasn't really enough to generate a ground effect. The air could really escape quite easily. But when you start throwing more into there, you then start to get this nonlinear effect in terms of the ground effect. Again, I'm not sure if this exactly is the case, but because I don't know what the exact dimensions are of the setup, but it could be the case. The other reason why is potentially because the Reynolds number. So these rotors, they're blades. They're made of these blades going around. And if you push blades faster, typically the flow will stay attached better, and it changes the angle of attack as well effectively. But all else being equal, it keeps the flow attached better because the Reynolds number increases. So then you get a more turbulent flow, and that can stay attached longer, so you get more lift being produced effectively. So that's another reason why we might be getting this nonlinearity here. But anyway, let's move back to the interference effects of the main rotor and the four corner rotors. So interestingly, from the amount of lift produced by the main rotor and the four corner rotors operating by themselves and not together, means that if you were to summate their individual lifts together and assume no interference, then at 50% power, the entire aircraft should be producing a 30.8 newton lift. At 100% power, the aircraft should now be producing 46.9 newtons in lift, but in reality, you actually get 28 newtons and 39 newtons respectively, which are both lower. So in other words, in reality, there are significant interference effects, and there is a 9.1% drop in efficiency of the entire aircraft when you have 50% power, and a 16.9% drop in efficiency at 100% power. So that means that as the power increases, the drop becomes greater. And that could have been why we get some of that nonlinearity we saw in the lift production as we saw earlier in the podcast. It is obvious from what we have just covered that a multi-rotor drone operation is highly nonlinear for a variety of reasons. And we have just seen that when you operate all these rotors together, you can expect up to a 17% drop in efficiency. Now, again, I'm pretty sure this is the extreme case because you have the major rotor like throwing air into the smaller rotors. But there may be the case where there is another configuration out there that's even worse than this. But I'm not too sure. This is the worst that I've found so far. So 17% drop in efficiency is quite bad. So that's what we have to deal with when we do drones. Okay, we do get the stability and an increased payload, but that comes at the expense of a reduced efficiency. So that brings us to the end of this podcast, my little analysis. I really liked it because we saw some really cool stuff and some interference effects, and these authors went through quite stringently different configurations to show us how they all interact together. So if you like this podcast, please hit the like button and subscribe or follow whichever platform you're on. And if you want to get better at aerodynamic theory and or CFD, check out our courses and link in the description. And if you want to make your experiments 2 to 4% more accurate, get yourself an Atmosphere Hawk. So it's an instrument that we make to actually measure the density of air. And the reason why this is important is because the density of air changes by 2 to 4% every day, and between days, weeks, months, and seasons, it's even more than that. It's 15% is quite normal. So if you don't take into account these changes in your experiments and CFD validation data, then your results are effectively quite wrong, because these days, even a 2% error is more than enough to make us draw wrong conclusions, and they hide trends that are actually there. We are interested in 2% changes, 4% changes, and changes in density mask that, and we can't see anything. And we may even be looking at things that aren't there, and we think, okay, they're actually happening, but because we haven't taken into account the changes in density, we haven't actually identified that error, and then we make wrong conclusions. So the Atmosphere Hawk gets rid of that error for you, and you can be more certain about your results and find more results. So you can write more papers and that. So you can find that instrument in the link in the description. And I'll see you in the next podcast. Peace, amigos.